Hello, everyone. Today we've got something a little bit different planned. For November 11th is the date of the Date IT Career Fair, and we're not supposed to have scheduled activities during the career fair because that's super important that you get a chance to go out there and talk to the potential employers. And I hope you're taking advantage of that. So instead, what we're going to do here is we are recording the lecture instead. Please watch the video. If you have any questions, let me know. And you can either talk next class or send me an email and we'll deal with any questions that you might have then. In any case, take a look and enjoy, maybe? Yeah. In any case, give it a watch. So last class, we introduced the concept of feature modeling as a way to understand the possible products that can emerge from a software product line. These models can be realized in a visual format, but underneath of that visual lies the ability to express a software product line as a formula in a propositional logic, defining a formal semantics of these feature models that we can analyze to prove that our product line will meet our requirements. In these formulae, all the feature names are interpreted as propositional variables. They can be true or false. If the feature has been selected, the variable evaluates to true. If it's not been selected for this particular product configuration, it evaluates to false. Pretty straightforward so far, right? In some cases, we'll also fill in numbers. And that might be where, for example, we can configure a different number of processes actively running at a time. But for most of our examples here, we're talking about Boolean variables. Yes, we're using this feature. No, we're not. Now, in this example, P and F are our features, and P is the parent of F. A mandatory feature, one where a feature must be selected, and in a mandatory feature definition, between a parent and a child, this corresponds to a logical equivalence when we're talking about the propositional logic. If we select P, we must select F, and this is bidirectional. If we select F, we also must select P as well, right? Whenever the parent feature is selected, so too must the child, and vice versa. An optional feature, we can choose to have this or not if we have the parent, is denoted as an implication statement, right? The implication states that parent P can be chosen independently from child F, but the child F can only be chosen if the parent P is selected, right? So if we select F, that means we must have selected P as well. This is not true in the other direction. If we select P, we don't have to select F, right? And that's the difference between mandatory and optional. The alternative constraint is that XOR choice. Choose exactly one out of many. In propositional logic, the first parameter is our parent, and that's followed by a non-empty set of child features, right? Of whatever number of child features we have. And when we map this in the propositional logic, this is a disjunction in which at least one child feature is selected when the parent is chosen, right? So if we look at this, what we have is child 1 or child 2 or child 3 until the final child, right? So in this case, if we had 3 children, this would be child 1 or child 2 or child 3, right? Must be chosen with P. So if we choose P, we must choose at least one child with his or. If we select at least one child, we must choose P. Then there's an and. For each child, Fi and Fj, not Fi and Fj. So what the second half of this is saying is that we can only choose one of these children. We can't have them in combination with each other, right? So in total, what this is saying is if we choose any child, we must choose the parent. And if we choose the parent, we must choose at least one child. And we cannot choose more than one child, okay? Not too bad, right? Now, our second here is this or constraint. It's an unrestricted choice. It's denoted by that filled arc between a parent and one or more children. And this is saying we can choose more than one of these, but we must choose at least one. We could choose all, we could choose two, at least one. Right. So in propositional logic, it takes in as the first argument the parent and then the set of children. And the formula is basically just the first half of this alternative. It's saying that, if we choose P, we must choose at least one child. If we choose at least one child, we must choose P. We can choose more than one. We can choose any number we want, right? We don't have that second half here that we had in the alternative. Now, these examples have been between parents and children, but can also be expressed between any pair of features. We could express constraints, right, between different features, whether they're the parent and child, or in completely different parts of our feature model, and those are our cross-tree constraints, right? We can also define additional arbitrary propositional formulae between the two features to express constraints. For instance, if we choose one feature, we must choose another, and so on. Now, what this leads to is the ability to analyze feature models and their corresponding product lines. Analyzing feature models is a great starting point for analyzing a product line because it is well understood and comparably simple. These analyses not only provide support for reasoning about feature models themselves, but also give us a foundation for analyzing the code of a software product line a little later on. All of the analyses we're going to discuss today are concerned with the feature model during domain analysis and feature selections once we're getting into the requirements analysis of application engineering. Now, among many other things, feature model analysis can give us answers to questions like, well, is a given feature selection valid for the feature model, right? Is this a valid product we can build given the constraints we've outlined? Is our feature model consistent? That is there at least one valid feature selection that can come from this model? Are there certain assumptions that hold true for feature models? Which features are mandatory? What features can never be selected? What are our dead features? How many feature selections does a given feature model have? Are two feature models equivalent? Do they define the same feature selections? And given a partial feature selection, what other features must be included or excluded? Or given a partial feature selection, what features should be selected to produce the product with the lowest cost, the lowest size, the best security, the highest performance? All of these are the types of questions we can answer by analyzing feature models and feature selections. And this is something that can be automated with tool support. This isn't something you necessarily have to do by hand. Each of these questions can be encoded as Boolean satisfiability problems that can be answered automatically using satisfiability or SAT solvers. The first analysis is that of feature model validity. A question that we can answer easily is whether a given feature selection is valid for a given feature model. And to this end, we can translate the feature model into a propositional formula phi. A feature selection is valid if and only if the interpretation of the formula, in which we assign true for every selected feature and false otherwise, is a valid solution to the formula. In other words, we substitute every variable corresponding to a selected feature with true and every other variable with false. The selection is valid if the overall formula, if phi, is true. This operation is computationally very cheap. It's linear in the size of phi. And the typical application of this analysis is during the requirements analysis phase of application engineering, where we're building a concrete product. When a user selects features, we can give immediate feedback whether the current selection is valid. We don't even need a SAT solver for this stage. We just can plug in true and false and see what it does to the formula. If the formula evaluates the true in the end, it's a valid feature selection. And if it doesn't, then there's a problem that we're violating some kind of constraint. And this is in fact implemented already in the configuration dialog for feature IDE, which you're going to use in assignment 2. And sorry, the screenshot's a little bit blurry. But next to the root feature, feature IDE indicates where the current selection is valid. So if there's a plus, that means the selection is valid. If there's a minus, it's not, right? Now, as we go along, we can click and select the features that we want to select with a plus. Right. Or at least the ones shaded in are ones that we've selected. Now, a red minus is going to appear and show us the features that we cannot select given our current selections based on the model. Right, and in this case, we can't choose, say, an undirected edge type because we chose directed, right? We can't choose them at the same time in our particular model. Or MST can't be chosen because we selected directed edges and it requires undirected edges. So you can start to see the constraints form between them. So here we show a subset of that feature model of that graph library and its corresponding propositional formula, right? So if we just walk through this, our root feature, just often the name of our system, in this case, graph library, right? That just appears on its own because it's always selected. It's always true, okay? Now, each formula is ANDed together in this. So we AND this together with edge type because edge type is mandatory. And here we have an XOR. We can only choose one of these, right? So we can choose directed or undirected and not both at the same time, okay? Now we get into this a little further and we have this little subset here with algorithms, cycles, shortest path, and MST, right? Now, this one is a unrestricted OR. We can choose one or more of these, right? We must choose at least one, but we could choose all three if we wanted to. So here's our formulas. Cycle or shortest path or MST implies algorithm. There's equivalence with algorithms. So if we choose the parent, we must choose one child. If we choose one child, we must choose the parent. That takes care of this particular bit of the subtree. Now we look a little bit further down, right? And here, this is choosing exactly one. So if we choose MST, we must choose one of the children. There's that or. And we can't choose both children at the same time. Now, we have a couple of additional constraints in all of this. With this, if we choose cycle, that implies that we also choose directed. Okay. If we choose cycle, we must also choose directed. So that's in here right here. And then in addition, if we choose MST, what that implies is that we choose undirected and weighted, and that's also embedded in here. So that's our entire formula. Once we choose our features, we can plug those selections in, and if it evaluates the true, we have a valid feature selection. If it evaluates the false, then we violated one of these constraints in there, or at least one of these constraints. So to check whether graph library, edge type, and directed is a valid selection, we substitute all the variables of phi with a corresponding assignment. All right, and we can do that here, and then we can, if we go through and solve all of this, this simplifies a little bit, right? So true, and well, true or false is true, and not true and false is not false, or in other words, true. And well, false or false or false, and equivalent with false, that's actually true. False implies false. Well, sure. Okay, that's true. False or false, equivalent to false, fine. And so on, right? And this ultimately, what this evaluates true is true, right? So this is a valid feature selection according to our model. All right. Now, this is an acceptable feature selection. Again, no stat solver yet, but we can make substitutions of true and false and check the results of evaluating the complete formula assignment. Let's try another one, okay? The next question we attempt to answer is, well, is there any valid feature selection for a given model? And from this, can we generate all the feature selections? We say a feature model is consistent if it has at least one valid feature selection. Otherwise, we say the feature model is inconsistent. In a model with many different cross-tree constraints, such a question is not actually trivial to answer. Adding contradictory constraints by accident is something that can easily happen. So naively, we could automatically check all possible feature selections until we find a valid one. This does not quite scale to larger models, and as a result, determining whether a feature model is consistent is an NP-complete question, or an NP-complete problem, meaning that there is no guaranteed efficient algorithm. In practice, we encode the question as a Boolean satisfiability problem, and we can use a SAT solver to compute the answer. So to ask whether a feature model is consistent, we simply determine whether its Boolean representation phi is satisfiable. Modern SAT solvers can solve many of these problems with great efficiency. They can also output the either the first valid feature selection they find, or they can just keep spitting out valid selections. SAT solvers use algorithms that can efficiently search the state space for a valid assignment, avoiding dead ends in that search. So let's talk about that process a bit. Right? I've mentioned the SAT solver thing a few times now. What is that? Well, Boolean satisfiability refers to the process of identifying a satisfying assignment that makes a Boolean formula resolve to true. The problem is defined over a formula written as a set of clauses in conjunction, in this case, right, x1 and x2 and x3, where each clause is formed by the disjunction of Boolean variables or their negations. So in this case, right, we have some variables, x1, connected as disjunctions within a clause, x1 or not x2, and each clause is connected by a conjunction and not x1 or x2, right? So conjunctive normal form connects the clauses in conjunctions, and within the clauses, we can use or and not. In Boolean satisfiability, the problem asks if there exists a truth assignment such that the complete expression is true. And what this means is that if you have a bunch of variables ORed together, then you have a clause. If you have several clauses ANDed together, then you have a formula or an expression that's referred to as a CNF formula, a conjunctive normal form, right? And here's another example here, right? We have variables, x1, 2, 3, 4, and 5. They're connected each of them are in clauses, which use or and not, and then they're joined together with and again, right? So here's what we're concerned about. We are interested in finding out if there's a Boolean assignment for each variable such that the formula evaluates to true. An example of a satisfying assignment for this formula would be 1 would be true, false, true, true, true. When we substitute each of those values into the formula, right, this evaluates ultimately to true. Right, sub these in, solve the expressions, and oh, look, all of those are true together. Great. That sounds pretty simple, right? It is in this case. This is one we can do by hand, but in the end, it's not. This problem can be NP-complete, and NP-complete problems get harder and harder as the problem becomes larger. So when the number of variables in the formula increases, when the complexity of those clauses increases, this problem gets extremely difficult to solve. Now, to get these expressions into conjunctive normal form, we often need to do a little bit of transformation into equivalent expressions that are in this form where the clauses only have ors or nots, and the clauses are connected with ands. Not too bad. I'm sure you've seen this before, but a little bit of review from the earlier class, right? We have De Morgan's laws, which turns not X or Y is the same as not X and not Y. Likewise, not X and Y is not X or not Y. So equivalent, but it gets us into a form that maybe is a little bit better for the type of expression we're concerned with. If you're going to distribute X through, if you have X or Y and Z, right? That becomes X or Y and X or Z. Similarly, if you have X and Y or Z, that can become X and Y or X and Z, right? And it's often good to remember that double negation just makes both negations go away, right? If you have not X, that's just X. Good to remember, but pretty simple, right? Many of the model expressions we looked at a little earlier had equivalence or implication in them. And we want to get that in the conjunctive normal form again, we have to do a little bit of refactoring into a better format. And it's not too bad if you think about what those expressions mean, right? So if we have an equivalence, we have X is equivalent to Y, right? What that actually means is that X implies Y and Y implies X. So that gets us an intermediate step, okay? But we still need to break this down a little further. Now, X implies Y is the same as saying not X or Y, right? So if X is true, Y is also true. But if X is false, Y can be either true or false, right? And so if we have something like X implies Y and Y implies X, well, that's the same thing as saying not X or Y and not Y or X, okay? So that's now an expression in conjunctive normal form. There's an or within the clause and an and between the two clauses. So there we go. That's going to help us a lot when solving for these models. Now let's go through an example of translating a model into conjunctive normal form. So here we have a simple feature model, right? And think back a little to our logic rules for the visual representation. Those are in the box as a reminder, right? What are the formulae that describe the model? Well, first, VOD is always chosen, right? And we can simplify that a little. What we're saying is it's equivalent to true. Its implied parent is true, but we can simplify that and just say it's always true. So VOD is always chosen. In this case, our video on demand. It's the root. It's mandatory, right? All right. So we move on. Now, here we have this filled arc, which means we choose one or more of the children. So if we choose VOD, that implies we choose record or play. And we can choose both if we want, right? There's no restriction. And if we choose at least one, if we choose record, we must choose VOD as well. If we choose play, we must choose VOD as well, right? So we've got that again, that equivalence. Now we move down again, right? And below play, we have this open arc, which means we can choose exactly one. This is an XOR. Okay, so what we have is mobile or TV implies play, and vice versa. If we choose play, we must choose at least one of these. If we choose at least one of these, we must choose play, and we can't choose both TV and mobile at the same time. Right now, we can distribute that a little bit. We can simplify this a little bit, right? Just so it looks a little bit simpler. And what we can turn this into is an equivalent statement is mobile is equivalent to play and not TV. And TV is equivalent to play and not mobile, right? So if we choose mobile, we must choose the parent and not TV. Similarly, if we choose TV, we must choose play and not mobile, right? So that's the same way to express that in a form that's a little easier to transform. Okay, now to form our complete formula, we then and these different clauses together. VOD and VOD is equivalent to record or play, and mobile is equivalent to play and not TV, and TV is equivalent to play and not mobile. Now, this is not quite conjunctive normal form yet, but it gets us closer. This is our basic formula, right? Now, what we want to do is do a little bit of massaging and transformation to get this into conjunctive normal form, okay? Now, there's parts of this that we need to work with. Any of these equivalent statements we need to transform. So when we have VOD is equivalent to record or play, all right, well, let's think about what this means. This means VOD implies record or play, and record or play implies VOD. Okay, great. Now we can transform this into not VOD or record or play and not record or play or VOD. Okay. Now we can of course start there, but we can also simplify this a little bit further, and that might make our lives easier. So we can turn this into not VOD or record or play and not record or VOD and not play or VOD. Now that turns this last clause into two, but it just makes our lives a little bit simpler, right? All right, so mobile is equivalent to play and not TV. All right, well, that means mobile or TV or not play and not mobile or play and not mobile or not TV. Once we go through and simplify this, similarly, this other one is pretty similar. This becomes TV or mobile or not play and not TV or play and not TV or not mobile. Okay. And if this isn't immediately obvious, go back to the couple slides before when we talked about the transformation laws and just try this out a couple of times yourself. And it just takes a little bit of practice. Now, many solvers use a format called Dimax, and this is not too complicated, but we first need to map feature names to integer identifiers. We can use any arbitrary integer we want, as long as we apply it consistently. So let's do that to our model, okay? So what we do first is we assign identifiers to each feature, and then we just step through 1, 2, 3, 4, 5. Not bad, right? Okay. Now we substitute feature names with their integer IDs in this CNF expression that we ended up getting. All right, so VOD becomes 1, record becomes 2, play becomes 3, TV becomes 4, mobile becomes 5. So we just get the formula looking like this. It's a slightly more compact expression. Okay. Third, then we store each clause in its own row and we omit the and symbols. So every time we have an and, we just create a line break instead in this file. And you can see here the mapping between these. So this line it has within it 3 different clauses, and so that becomes 3 lines. Similarly, another 3 lines, another 3 lines. And in any case we had a negation symbol, that becomes a minus sign in this Dimax file we're creating. Now we remove the disjunctions, the or signs, right, within our file. So this -1 or 2 or 3 just becomes -1 space 2 space 3. Okay. And also we add a certain header. This header has C for any line with comments. This particular line indicates that it's a CNF format with 5 variables and 10 clauses, right? And this just gives the solver a bit of information to work with. So now we can plug this file into a common SAT solver. For instance, picosat is a pretty common Python SAT solver that's pretty easy to use. So great, we have this model. Now we can use the SAT solver to try and satisfy it. Now, as I mentioned, the basic idea is to find out if the expression is solvable. Is there an assignment to the Boolean variables that results in the entire expression, every clause evaluating the true? If yes, this will return the first assignment it finds that satisfies the expression, right? So in this case, a satisfying assignment is true for everything except the last one, which if we scroll back just a little bit, our last one was mobile. So if we skip mobile, I see, yeah, so we could choose VOD, record, play, and TV would be valid. Now, similarly, we could choose VOD, record, play, and mobile. That would also be perfectly fine, but that one satisfying assignment here. Right. And this returns, the SAT solver returns a satisfying assignment if it can find one. Depending on the SAT solver, it can also try and compute all possible solutions it can find within a time bound. Before it times out, it'll return everything it finds. And it can also try and follow other constraints you give it. If the model is provably not satisfiable, So we didn't just get a timeout, but the solver also figured out that it cannot be solved. The solver may also return information on why it's not satisfiable if the problem can be summarized down to specific clauses. Okay, so now at this point, I'll have an activity if you want to try it out, to try and just analyze a few of these models by hand and find valid feature selections. So this activity is on Canvas in the files area. Also on the slide, there is a bit.ly link, bit.ly or bit.ly/3bvwmzc. Right? If you go there, that'll take you directly to the activity. So we consider here we have 4 different feature models, and if you I'd start with A and B, and then if you want a little practice, have a little time, continue on to C and D as well. And for each of them, translate the feature model into a propositional logic formula. Note that the expressions next to A, B, and D here are additional cross-tree constraints. So in this case, choosing E or F implies we choose D as well. Even though D is normally an optional feature, we have that constraint in place. Now, once you do that translation, try and come up with 2 valid, and if you can, up to 2 invalid feature selections as well. And then determine whether the feature model is consistent. If there are any valid configurations, it is consistent, but if there are no valid configurations, then it is not. And if it's not consistent, try and identify a reason why that would be the case. Okay, so I would recommend now that you pause the lecture, try this out, and then when you come back, we'll look at the solutions. So welcome back. Hopefully you tried this out, and if not, well, try it out sometime to make sure you know how to do this by hand. All right, so for model A, we can translate this into the following formula. All right, so A is just there, it's true, it's our root. B is an optional feature, but if it's chosen, that implies A, so B implies A. C is a mandatory feature, right? So C is equivalent to A. If we choose A, we must choose C. If we choose C, we must choose A. And D is another optional feature, so D implies A. So if we choose D, we must have chosen A. This is not true in reverse. If we choose A, we can skip D. And for the next line, right, this is our XOR choice. So in our next line, if we choose C, we must choose at least one of the children, and we can't choose both children at once. And then we have this additional constraint that if we choose E or F, we must choose D as well. Okay, so we can, for this one, we can come up with both valid and invalid choices. For instance, if we chose every feature at once, that's perfectly, or sorry, if we choose everything except E, rather, that's fine. If we choose A, B, C, D, and F, that's great. Or A, B, C, D, and E, that's also fine. Or we could choose A, C, D, E, and that's also great. That obeys all of our constraints. Now, invalid, we can't choose everything at once. We must choose only one of these children. Or if we chose either E or F and skipped D, so if we chose A, B, C, E, that's also invalid. But is this consistent? Yes, it is. All right, our second model. A, again, the root, always there. B is a mandatory feature, so B is equivalent to A. If we choose A, we must choose B. If we choose B, we must choose A. Now C is optional. If we choose C, we must have A, but not vice versa. Likewise, D is optional. If we choose D, we must have A, but not in reverse. And now we move below. E and F, this is our XOR again, right? If we choose C, we must choose one of these, but only one of these. And then G is optional. If we choose G, we must have chosen D as well. Now we also have 2 additional constraints. If we choose D, we cannot choose B. And if we choose E, we cannot choose G, okay? So there are some valid configurations, but these constraints are pretty restricted, especially here because B is a mandatory feature, but that effectively means that we can't choose D. If we choose D, we're not allowed B, but B must be there. So D and G can never be chosen effectively. right? This is a model that we probably want to go in and change later because of that dead feature. But in any case, A and B is a valid selection. That's our minimal model. Or we could choose A, B, C, and F, and that would be fine, right? That doesn't get into this thorny business where if we choose E, we must have G, but we can't because that means we need D, which we can't because B is present, right? So effectively, D, E, and G are all dead features here, and this model is not a very good one. That we need to take a serious look at this because there are features in place that we just can't have. All right, C. A must be here again. Now, below that is this filled arc where we can choose one or more of these. We must choose at least one. We could choose two. We could choose all three, right? So B or C or D it is equivalent to A. If we choose A, must choose at least one. If we choose at least one of these, must have A as well. Okay, now if we go below that, E is a mandatory feature if we choose B. So if we choose B, we must have E. If we choose E, we must have B. They must come as a pair. Right? Now below D, there's two optional features, F and G. So there's no arc. These are separate optional features. If we choose F, we must have D. If we choose G, we must have D. If we choose only D, we don't necessarily have to have either of those. We could choose them optionally. So valid features or feature selections. A and C is great. That's a good minimal one. We could have A, B, C, D, E, F, G. That'd be just fine as well, right? There's nothing stopping us. Now, if we choose A, wait. A, B, C. Oh, I see the problem. I was about to say that I made a mistake. No, this is actually fine. This is why you proofread things before you give presentations. Okay, so ABC is an invalid selection because E is mandatory if we choose B, right? We can't ignore E. So ABC is invalid because E would also need to be there. Likewise, ACE is invalid because that's omitting B. If we choose E, we must have B. Similarly, if we choose B, we must have E. Okay, so both of these invalid ones omit one of this pair. And it is consistent, but again, just remember that B and E need to come as a pair. One more example, okay? Here we have this model. A must be present again. B is an optional feature, so if we choose B, we must have A, but not in reverse. If we choose A, we can ignore B. C is a mandatory feature, though. If we choose A, we must have C. If we choose C, we must have A. Okay, they must come as a pair. Stepping below this, if we choose B, we must bring D with it, right? So if we choose D, we must have B. If we choose B, we must have D. Those must come as a pair. Now below C are two additional optional features. If we choose C, we can choose E. If we choose E, we must have C. If we choose F, we must have C. We have two additional constraints. If we choose F, we must have E. And if we choose D, if we choose D, we must have E. If we choose E, we must choose D. So there's an implication on F and E. If we have F, we must have E, but if we have E, we do not have to have F. There is an equivalence for D and E. If we choose D, we must also have E. If we choose E, we must also have D. Those must come as a pair as well, if we choose any one. Okay? So this is, again, a consistent model. AC would be a valid selection. Or we could have, say, A, B, C, D, E. That would be just fine. And we skipped F. That'd be fine. But if we choose A, B, C, D, that's not valid because if we choose D, we must also have E as well. Okay. Similarly, A, C, F is not valid because if we choose F, we also must have E. So this is consistent, but just remember if you choose F, well, as a result, what you would need is E, D, and B altogether because of the total sum of these equations or of these constraints. Okay. Hopefully this makes sense. If you have any questions, please let me know. Now, you will probably not appreciate how difficult solving an NP-complete problem such as SAT is until you understand how the solvers work a little bit. How do we find the assignment? Well, first thought, you could enumerate all possible 1 and 0 configurations and verify each of those. Try everything. Will this work? Maybe not. This would be fine for small problems, but as the number of variables becomes large, enumerating all possible combinations becomes impossible. Generally speaking, if you have n variables, that's an exhaustive search requires 2 to the n checks. If you have 5 variables, then there are 32 possible configurations. Not bad. We can do that by hand, but if you have 1,000 variables, then you need 10 to the 301,207 or 29th power. So yeah, that's not happening. Instead, these solvers rely on what we call complete or exhaustive search methods. These methods guarantee finding a solution if there exists one, but that doesn't mean checking every possible configuration. They use some clever methods to trim the search down and ignore paths in the search that won't lead to fruitful solutions. There are many different approaches, each with their own heuristics, but there are two main algorithms that we start with called branch and bound and DPLL, or the Davis-Putnam-Logman-Loveland, named for the creators, algorithm. We'll discuss each of those, but they start with an expression in CNF, right, and examine what could happen to those clauses if we assign a value to a variable. What happens if we assign x2 to be true? If that changes any clauses to be false, making the whole expression false, we don't apply it. And if it doesn't, well, maybe we will apply it and continue until the whole thing is satisfied. There's a bit too more to it than that, but that's our starting point. So let's talk about each of those quickly. Our first complete search algorithm is the branch and bound algorithm. This algorithm is conceptually simple. Set a variable in the Boolean formula to a particular value, apply that value to the formula, and check to see if the value satisfies all of the clauses that it appears in. If so, assign a value to the next variable, and so on. However, if setting a value unsatisfies a clause, then a backtracking step, a bound, is initiated, and the other possible value is applied. This process prunes branches of the form Boolean decision tree. Now, although we have reduced the number of checks we performed, it does not mean that the problem has become any easier. It's still hard to solve, and it's an NP-complete problem still, but by trying assignments carefully, we get to a solution more quickly, generally without trying everything. So, first of all, we have a sample expression here, right? Not x2 or x5, and x1 or not x3 or x4, and x4 or not x5, and x1 or x2. So we're going to first set a value of false to x1. That inserts a 0 into clauses 2 and 4, or false into clauses 2 and 4. It doesn't satisfy or unsatisfy either clause just yet. So we'll continue. Next, we insert a value of false for x2, right? So we put this in as a 0 in our expression. And this satisfies the first clause, which is great, but it unsatisfies the fourth. False or false is false, and that's bad, right? So we stop there and we backtrack. And we're going to instead try and set that to true and see what happens. And that's actually going to satisfy the fourth clause, which is great. And we can continue this process with all the variables until the complete formula is satisfied. If we hit a dead end, or applying either true or false unsatisfied something, then we'll backtrack again to the assignment before that and see if we can change that outcome. So this is almost like a depth-first search in a graph. We go as deeply as we can in the form decision tree, and we backtrack when we cannot make any additional assignments without unsatisfying something. Another common complete method is this Davis-Putnam-Logman-Loveland, or DPLL algorithm. And it's very similar to branch and bound, but there's a slight difference which makes it a bit more powerful. And the way it works is this: you select a variable or its negation, assign it a value if the result is true and satisfies the clause, then we remove all clauses containing that variable from the formula, creating a simplified formula. On the other hand, if the literal is false due to its negation, We remove only that specific variable from the clause. And so far, this is sort of like branch and bound, except that we're looking at from the point of view of these clauses and trying to simplify them. And we recursively perform this simplification until we can find a solution. To make this even better, if a clause contained a single literal, then we assign that literal true and perform the same procedure. And this is something called unit clause elimination. And you can imagine how this would have a cascading domino simplification effect on the expression. As more variables are eliminated from clauses, the more clauses turn into simple unit clauses with one variable in them, and we identify those and get rid of them as soon as possible. Right? So here we can start with the same example again, and if we assign a value of false to x2, then that first clause is rendered true. Right? So we scan this and we see, hey, there's a not x2. That's something we can very quickly solve. We set it to false. That becomes true. And we simplify the expression, right? Now we can eliminate this, this clause entirely because it's true. Okay? And back here, this simplifies out to just being x1. So we have a slightly simpler expression than we started with. Okay. Next, we could try setting x1 to true because we see x1 is this unit clause back here, and we can quickly eliminate it. And look, that takes care of expressions or of clauses 1 and 3, leaving us just clause 2. And from this point of view, it's pretty trivially solved, right? If we set, say, x4 to false and eliminate it, and then we can set x5 to false, and it becomes true. Right, so we end up with true for x1, false for x2, and false for x4, false for x5. All right. Next, we can talk a little bit more about some other analyses you can perform using the same kind of procedure. Now, a domain engineer typically knows certain facts that must hold in their domain and that should also hold in the feature model to ensure the system we build is a valid one. For example, in the graph library we've been using as an example, we know that feature cycle requires the feature directed. This fact must be embodied in the feature model. The feature model must not allow any selection to violate that dependency, or there will be issues in the corresponding system. So in the graph example, the constraint is pretty easily fulfilled. It's even stated directly as a cross-tree constraint in the feature model. However, especially in larger models, it's really easy to forget constraints or not even realize they should exist when you first create the model. In those cases, we want to ensure the model meets our stated properties. If it does, it's more likely the systems we build in the application engineering phase will ensure that we'll meet the properties, we'll meet the requirements we have of them as well. So to test a feature model, we check an assumption encoded as a second propositional formula we'll call it psi. For instance, if we choose, say, the feature cycle, we must choose the feature directed as well in our feature model, right? So we have phi, and that's our model expression. And we have any additional properties we have as well. And what we can do, we can check that the feature model implies the assumption, right? Or phrased a little differently, we check whether we can somehow satisfy the feature model being met, like a valid feature configuration, and the requirement not being met at the same time. And if that's the case, that means we have a feature selection that can violate that requirement. And that means the feature model is incorrect, as there's a valid feature selection that does not satisfy a requirement we have over. In a practical setting, a domain expert can test a feature model by creating a list of assumptions that the feature model must satisfy and follow this process to search for violations. So here we have our graph library again. To test this model, we want to state constraints that may not already be encoded into our formula. And we can state those as a set of propositional formulae. So for example, here are some facts that we might assess. The first two of these state that here, if we choose Kruskal, we must choose weighted as well. If we choose prim, we must choose weighted as well. Essentially, what this is saying is that any minimum spanning tree algorithm requires weighted graphs. Okay, not too bad. The third states that both prim and Kruskal must never be present in a graph product that we choose. Right? Those two must never appear together. And we could also choose, for instance, that if we choose weighted, well, that implies we must choose MST as well. So to check whether these are true, we can assess whether we can get a valid feature selection without each individual one of these being met using a SAT solver. Now, in this example, facts 1 through 3 are true of our any product, but fourth is actually false. If we choose weighted here, right, MST implies that we must have undirected and weighted at the same time. If we choose weighted, well, we don't necessarily have to choose MST as well. MST implies weighted, but not in the other direction. You could choose weighted and cycle or shortest path, right? So that fourth fact is not necessarily true of our model. And we want to assess whether that is a requirement we need to meet. And if so, well, we could throw this in as an additional cross-tree constraint, for example. Maybe it's one we didn't think of earlier when we were forming the model. Or we could decide, hey, maybe that's not a requirement that makes sense. Maybe it's fine to choose weighted, but not choose MST as well. That's something to think about. Next, we might want to know if a feature is dead or mandatory. A dead feature is one that's never used in any product. In contrast, a mandatory feature is always used in every product. So given a feature model, there is at least one valid feature selection for a feature if and only if the phi are our propositional formula over the whole model and the feature we're interested in is satisfiable. Okay. So what we're doing is feeding a formula into our SAT solver saying that F must be true in the resulting feature selection. And if it comes back and says there's a feature selection, well, that means that there are feature selections where F are chosen. Similarly, if we plugged in phi and not F, that comes back and tells us there are feature selections possible without phi. So a feature is dead if there is no valid feature selection with that feature in it, right? If this is not satisfiable, or if phi and F is not satisfiable, that means the feature is dead, right? There's no possible way to select it. A feature is mandatory if we cannot satisfy phi and not F, right? If there's no feature selection possible without F, then that's a mandatory feature. And we can simply iterate over all of our features with the SAT solver in this idea, and it can come back and tell us which of our features are dead and which are mandatory, right? Typical feature or typical application of detecting dead features is to report warnings in a feature model editor. For instance, feature ID might come back and tell you, hey, this is a dead feature, do something about that. And if there is a dead feature, we can alert the developer. That means no possible product will ever have that feature, which makes us ask why it was there in the first place. It's likely we made some kind of mistake in our constraints that results in that feature never being selected. Also, an editor may issue a warning of a false optional feature if our analysis reports the feature that we modeled as optional is actually mandatory in all feature selections, if it's always there. Dead and false optional features could be considered code smells of feature models that indicate possible mistakes we've made. It's really easy to do when we evolve a model over time, so it's good to perform this kind of analysis. So here we have our graph library again, and this model actually has no dead features in it, which is great. Graph library and edge type are mandatory. right? The root is graph library. That's needed no matter what. So that's kind of trivially mandatory. Of course, we know it's there. Edge type has a filled circle, or has a, an unfilled circle. So we must choose. Let's see, edge type is, yeah. So edge type is this filled circle here. Edge type is mandatory. We must choose it. Right. So we know it has to be there. That also makes feature undirected mandatory by adding a constraint. Or sorry, I'm just tripping over this slide today. That's why you need more coffee, right? So we could choose to make undirected mandatory by adding a constraint to this, right? And if we did that, then directed and cycle would become dead features. All right, that makes more sense. Sorry about that. Again, I'm recording this first thing in the morning, need to have your coffee, right? All right, so as a user chooses features during feature selection, some features may no longer be selectable. They would invalidate the feature model, and others might become required. A good editor can provide tool support to infer feature selections by automatically disabling or hiding unavailable features and selecting implied features automatically. And this is a mechanism called constraint propagation. All right, as we make selections, we propagate through constraints and we see what else is possible. So far, we've specified feature selections as a set of features and assume that all features not within the set are deselected. In contrast, in a partial selection, we've not yet made a decision about all features. This is normal, as product configuration and derivation is often an incremental process. So there's three possibilities here. A feature is selected, a feature is deselected, or no decision that has been made yet. As a consequence, we specify a partial feature selection with two sets. A set of selected features, right? So a subset within our full set of features that have been selected, and a set of deselected features, again, with a subset of our full set of features that we cannot choose. And with a null set being the in common between the two, right? We can't have something that's selected and deselected at the same time. Determining which features must be selected or deactivated given a partial feature selection is a similar process to detecting dead or mandatory features. We encode a partial feature selection with the sets S and D as that predicate PFS S, D. Right, and so a partial selection is valid if we can satisfy phi and the part and what we've already pre-chosen as being selected or not selected. Right, so if we can get back a feature selection from the SAT solver that satisfies all the constraints in the model and meets what we already partially selected, well, that means we have a valid partial selection. Okay. Now we can say a feature F is deactivated or no longer selectable if, given our partial selection and the feature model, we cannot get a solution back to phi and the partial selection and F being true. We can also say that F is now activated. It must be chosen if, given our partial selection and the constraints, we cannot satisfy phi and the partial selection and not F at the same time. That means that now, because of our choices, we must include F. Okay, so here's our graph library again, and let's say we selected cycle. Okay, well, that's going, due to the implication of cycle implies directed, selecting cycle now suddenly means we've also activated directed as well. We must choose it as well. Okay. Directed and undirected are mutually exclusive. So after we've chosen cycle, well, we've selected directed, which also propagates through, meaning we can no longer select undirected. It is deactivated as a result, right? Now, given two feature models, two entirely separate feature models, we'll call those phi1 and phi2. What is their relationship to each other? Does phi1 define the same set of feature selections, the same products as phi2, or is phi1 a generalization of phi2, meaning that The set of products of phi1 is a superset that includes those of the second model and more. Or conversely, is phi2 a specialization of phi1, which means it's a subset of the products of phi1. Those questions about the relationship between two different feature models that are similar can arise early on in modeling because you might be considering different options for your feature model. And you might want to compare the two different models you've come up with to make a choice in the end. When a designer edits a feature model, they may want to know if the changes have altered the set of existing valid products. And enlarging the set of products may be acceptable, but eliminating products, especially those that we're already advertising, might not be. However, except for trivial cases like adding or removing a single feature, that relationship is not always obvious between two models or two versions of a model. Even simple feature models are of sufficient complexity to make analyzing the relationships by manual inspection often quite difficult. We have 4 relationships we might want to identify. We show them here. A feature model refactoring preserves exactly the set of valid feature selections, whereas a specialization removes valid selections without adding new ones, and a generalization adds feature selections without removing any. All differences of both add and remove valid selections are classified then as arbitrary edits. Okay, so again, refactoring preserves the same feature selections. We just made some changes, but in the end, the model is technically the same, which is sometimes great. Sometimes that allows simplifications to the model without changing what products we can have. Generalization means we added products. So we went from defining this set of products to a larger set. A specialization means we now offer a smaller set of products. And an arbitrary edit might add some products but delete others at the same time. Okay, great. One approach to classify the relationship between two feature models is again based on Boolean satisfiability. Two feature models, phi1 and phi2, are equivalent when their propositional formulas are equivalent as well. That is, phi1 is equivalent to phi2, and operationalized for a sat solver, right? We can say that models are equivalent if their formula are not equivalent. So if we feed into the model not phi1 is equivalent to phi2, if that's not satisfiable, that means the models are equivalent to each other. Similarly, phi1 is a specialization of phi2 if phi2 implies phi1 is satisfiable. If we can return back an assignment that shows that phi1 or phi2 implies phi1, and if phi1 is a specialization of phi2, then in the reverse direction, that means that phi2 is a generalization of phi1. It's a superset, including all products of phi1 and others. And stat solvers can compare those models, of course. So here we show two feature models, right? A and B. And we, of course, have the propositional formulas for both of these. And what we might want to do with our stat solver is prove that that B is equivalent to A, right? That these are technically the same model, just expressed in different ways, by finding that no assignment can violate this formula. And the stat solver can go in and find this out, right? It can find out, hey, are these equivalent or not? Now, there's a little bit more we can do with this kind of analysis. So in the last section, we focused on the problem space with feature models and feature selections. Now we investigate the mapping from features to code. That is the mapping from the problem space to the solution space. By leveraging the same analyses in the previous section, we can look at how to detect unused modules, dead code and preprocessor-based implementations, and look at issues regarding build systems, for example, that can complicate these analyses. So we could look at things like which code fragments are never included in any product, what code fragments are included in all products, what features have no influence in the product portfolio at all. So as an example of this, we could look at finding dead code, fragments that are never included in any valid feature selection. Dead code can be an indicator for an incorrect mapping or an over-constrained feature model. So if we look at the model and the corresponding code here in this slide, this is a preprocessor-based implementation. If we choose feature A, line 3 is included. Now, as we move down, if we include feature B, line 5 is included. And now we have this else, right? And this else is associated with feature A. So if we don't choose feature A, line 8 is included. Okay. Now, line 5 is only included if A and B are selected. But if we look at the feature model, it's an exclusive OR. It says we can only choose one of these. So that means line 5 can never actually be included in our product line. The developers were likely unaware that A and B were defined as mutually exclusive, or the feature model was too strict, and maybe both features actually could be optional. We could have an issue with our model or in our code, and this needs to be resolved as B cannot actually be used right now without requiring A as well. Likely the model is at fault and the code is fine, but we need to resolve this. To identify dead code, we need to reason about the mappings from features to code. Formally, we describe this mapping as a function from code fragments from the set C of all code fragments to sets of products represented by feature selection. So we map each code fragment to the set of products in which it's included. As a nice compact representation of large sets of feature selections and corresponding products, we use what we call a presence condition, a propositional formula representing a set of feature selections. This is in line with the propositional formula representing the set of valid feature selections in the feature model. A presence condition is a Boolean expression defining the feature selections in which a particular code fragment is present. We use a function PC of C here to denote the presence condition of a code fragment in the form of propositional formula. So for example, line 3 is the presence condition A. It is included in all products where feature A is selected. Line 5 has the presence condition A and B and is included in all products with features A and B. And line 8 has the presence condition not A and is included in all products that do not include feature A. We can do this for any arbitrary code selection. So the presence conditions for lines 3 through 5 are A and B. And to include all 3 through 8, that means A and B and not A, which means we can't include all of lines 3 through 8 in any particular product, right? As we'd have A and not A there. That's impossible to meet. So a code fragment is dead if it is never included in any product of a product line. Since the representation of the feature model as a propositional formula phi represents all valid feature selections, all valid products, a code fragment is dead if and only if the conjunction of presence conditions and feature model is not satisfiable. If there's no feature selection that's both valid according to the feature model and that fulfills the presence condition. In our example, we have the presence conditions A and B, and not A for lines 3, 5, and 8 respectively. And the predicate of the feature model is phi of the program and A or B and not A and B. So putting this together with line 5, A and B is not satisfiable, right? Because we end up with not A and B and A and B at the same time. So that helps us indicate that line 5 is dead code. In a similar manner, we can detect code fragments that are included in all products. The code fragments, they're mandatory. And a code fragment is mandatory if phi implies the presence conditions, or in other words, phi and not PC of C is not satisfiable. If it comes back and says that we can't find a product without meeting the presence conditions for C, that means that C is mandatory. Right now, in that simple example we had in the last slide, there were no such cases. But if we go back to our graph library, we see the edge type feature is mandatory in the model, right? If our code matches that model that presents conditions for edge type, will ensure that the corresponding code fragment is mandatory as well. Otherwise, there might be a mistake in our code. So let's wrap up. Feature models can be expressed as propositional formula based on the model and the cross-tree constraints, and valid feature selections result in that formula being true. Sat solvers can identify valid configurations, and if none are found, the model is inconsistent. But this idea of plugging these formula in different ways in the sat solvers enables a lot of different analyses. We could see if certain properties in the model were true. We could look for dead and mandatory features. We can look at the propagating effects of partial selections, and we can compare different models. We can also look at the mapping between models and code to do things like detect dead and mandatory code and all sorts of other things. But this gives you a taste of the types of analyses that can be performed. Now, next class, we'll be back in person and we'll talk about variability implementation. We'll start to talk about simple mechanisms for implementing variability into a system and the properties we might want to see out of a good variable system that can evolve over time. Assignment 1 is due on Sunday. Hopefully you are well into that and you've gotten approval from your supervisors and have meetings set up and all of that, right? Otherwise, work on that and reach out to your supervisors and me if you have any questions. Also, start thinking about assignment 2. That's going to be due the following Sunday on November 21st and focuses on feature modeling and analysis for mobile robots. We've now talked about all concepts covered on that assignment. So if you are finishing assignment 1, just to go ahead and start into thinking about assignment 2 now. And again, let us know if you have any questions. And we will see you back in person next class.